Okay, so our next speaker going to be Professor Kaushik Roy. Professor Roy is Edward G. Tiedemann, a junior distinguished professor of electrical and computer engineering at Purdue University. He received his Bachelor of Technology from Indian Institute of Technology, Kharagpur, PhD from University of Illinois at Urbana-Champaign in 1990. His current research focuses on cognitive algorithms, circuits, and architecture for energy-efficient neuromorphic computing, machine learning, and in neuromatic devices. Yeah, Professor Roy.
All right, thank you very much. So what I'd like to do today is talk about cognitive computing, but really from sort of the robustness and security challenges point of view. Initially, the last time I gave the talk, it was more on the in computing side of things, learning, neuromorphic computing. So this is going to be slightly different. We all know that, let me see if it works. Yeah, deep learning certainly has made a huge amount of progress in the recent past. And you open up any tech news, you see, all these different news items, right? And the one that came out recently was kind of interesting, and it tells you how far AI has gone. Really, AI won an art contest, and the human artists are furious about it. So that really tells you that a huge amount of progress has been made. But certainly at what cost? It's still AI is still a black box. And if you really think about it, sometimes we don't know why it works well, and sometimes why it doesn't. So is there a way of really finding out? And people have been looking at it from different points of view: digital signal processing, information theory, and so on. So the question, of course, is, can I really try to unravel the black box of AI? Sure. Oh, it's not changing? Okay. So I'll have to go over it again. Yeah. I mean, I can start from here, or? Okay, that's fine. All right, so the question, of course, is how do we unravel the black box of deep learning? And can we really come up with more robust learning algorithms? Can we look at the interplay between accuracy, robustness, and efficiency in some ways? And that's what we're going to be looking at. Again, this is a vast field, and I'm going to be really taking a few examples to show some of the vulnerabilities and some of the interesting things that one can potentially do with AI, and and some possible solutions. So if I were to really look at the modern deep learning pipeline, you certainly need some data set, right? And then finally some sort of a deep model, where in the model, basically, during the training time, you come up with the thetas, which are basically the parameters or the weights of the neural network to learn, and you actually have a loss function that's there at the output, and you try to minimize the loss, as in the previous talk we heard. And then in the deployment, you actually have a test data set that's shown here, and hopefully you get a very good prediction out of your test data set. Now, the question, of course, is saying, what are the possible problems or the vulnerabilities that we have in this deep learning pipeline? So if I look at the data side of things, there's some interesting things. I mean, there could be mislabeled data, and we'll talk about that. There could be actually some data that, long-term examples, people might have poisoned the data and so on. So the question, of course, is, can I really detect such data poisoning or mislabeled data? On the other side of it, if you really look at the training, there are several other kinds of vulnerabilities that I'm not going to be talking about today. Optimization, when you look at optimization, semi-supervised learning, and model architectures, there could be different kinds of optimization vulnerabilities. And finally, after deployment, there are other issues that one has to really look at. Is it possible that some of these long tail examples are out of distribution inputs or adversarial inputs, and we'll talk about that. Would that lead to any problem? And I'll give you some examples of that. And to that effect, actually, we've been looking at each of those areas, and I'm going to focus on mainly the input part of it, and some of these deployment. So to that effect, let me get started with some of these adversarial examples. And you might have seen some of these examples earlier, but just for the sake of completeness, I'm going to talk about some of these adversarial inputs. Now, in general, let's say that I've trained a deep neural network. And I've trained it, and I've trained it well. And I show this macaw. It is trained to learn it's a macaw. And when I show this macaw, it gives you a very high confidence that it's a macaw. Now, what I end up doing is I actually come up with some crafted noise, let's say. And if I have this crafted noise and I add that to that noise to a human, it's still a macaw, right? It's possibly you don't see any changes. However, now my deep learning model, and I'll tell you how I can do that, deep learning model says with 80% or 90% confidence that it is actually a bookcase, and it has no similarities with a bookcase, right? So these are actually interesting vulnerabilities that one can potentially look at. So these kind of adversarial attacks, which are called adversarial attacks, can have catastrophic implications. Think about it that, in driving scenarios, self-driving scenarios, you have an image, the prediction of the image which is shown on the right, but if I have an adversarial image which looks very much similar to that image that's shown there, and then the prediction is that there are no human beings over there. So if that happens, of course, there can be collisions and other kind of catastrophic problems. And these can potentially happen. And I'll give you some examples of it. So the question, of course, is how do I come up with these adversarial examples? It's a good, interesting way to come up with such examples. Now, when we train a neural network, in general, what we do is we actually show a bunch of data. And then at the output, I say, hey, yeah, I've shown a cat. Is it still a cat? If it's not a cat, if it's showing as a dog, there's a loss. And can I back propagate that loss to the network, update the weights so that a cat is a cat and a dog is a dog? Now, what one can also do is, and interestingly, take a train network. And after taking the train network, which has these the weight parameters which are given, with thetas which are given, what one can potentially do is now you take you can show the dog, and then you forward propagate through the neural network. It shows it's a dog, but intentionally, let's say you try to make that dog to be a bookcase. Now you say, hey, if it were a bookcase, can I back propagate that loss and maximize my inputs in such a way, right, so that I don't change the weights. I only change the input in some way so that with minimal changes to my input, can I make the dog to be a bookcase, as an example. And that's what you try to do. Given learned parameters which are there, you find some delta 1 through delta n, which are for the inputs, which is basically some sort of a noise that you try to come up with that maximizes loss over the training data. So this time you're not changing the weights, you're changing basically your input, right? And to that effect, if you do that, this basic idea is that, hey, this is a trained network. I go through a forward pass, I go backwards, but what it really do is I don't change the weights, I end up changing the input minimally as possible. And then I come up with that delta, that noise that I just talked about. If I add that noise to my, if I add that noise to my now macaw, that macaw is probably going to be a bookcase, as I shown earlier. So these are really vulnerabilities. The question, of course, is can I really now try to understand those adversarial examples in a little bit better way? And so if I try to understand it, I can try to say, hey, can I draw decision boundaries? And that's what I end up doing in my neural network, that I have these red balls, the blue balls, and the green ones. And I'm trying to actually come up with a decision boundary so that, hey, the red balls, when I have a test input that comes in, a red ball which falls in that sort of hyperspace, I can call them to be, red balls. So now, interestingly, what happens is that these, the best generalization that you can do is the extrapolation of this boundary of these, hypervolumes is a result of the linearity that yields the generalization. But one can potentially also think of misclassification, as I mentioned earlier. So what one can do is one can take some of these examples which are sort of close to that boundary. And if I can push them in some ways, and that's what I was trying to do by adding some adversarial noise, then now blue becomes green, right? And that's what we try to avoid if I can. Now, question, of course, is in that case, can I generalize better? So what are the ways of generalizing better? One way of doing that is that you generate a bunch of these adversarial examples. You take a trained network, you generate a bunch of these adversarial examples, and then you train the network with those adversarial examples that say, hey, the Macau that I had actually become a bookcase. Now I'm going to make this bookcase to be back to a Macau again in my training. Right? And if I can do that, it's in a tedious process. You have to generate a large number of data, data points. And if I do that, then possibly you can get a reasonably good in a neural network for both clean and adversarial data. But turns out that is it possible that I can use something else? I mean, that's a tedious process. And can I learn in such a way that I probably are not going to see some of these adversarial examples? We humans don't really see these adversarial examples, right? So the question, of course, is, hey, can I now take some cues from how we learn and whatever little that we know from neuroscience? So to that effect, people have been talking about the active vision system. And the active vision system is basically a two-stream hypothesis that's usually, they talk about. One is called the dorsal stream, which is basically guiding the functionality. It's also called the where stream. And the other one is basically the ventral stream, and it's called the what stream. We'll go into that, what and the where stream in just a minute. We can potentially think of, and I'll just go into that in a minute, is somewhat like what we do. We can focus on things at a particular object, and it can blur the rest of the things out, right? And then I have rapid eye movements, my saccades in some ways, and then I go from one object to another object. So that's going to be my where stream versus the what. What object am I looking at? So just to go into a little more details, we have the human eye as part of the human eye is called the region called fovea, which captures the most details, responsible for sharp central vision, which is necessary in human for any activity with where visual detail is of primary importance, right? And this is an example of it. I mean, I can focus on a particular area, the fovea, which is all the details are shown there, and the rest periphery around it is sort of blurred. Again, we are not able to change our focal length that much, but then again, if you can potentially think of looking at this kind of diagram shown on the right, the stop sign, I can actually have my glimpse sizes to be different so that I can get various details. So the question, of course, is, and the other side of it, the where stream that you can potentially think of is what's the saccade is. Saccade is a quick movement of the eye between different fixation points, and human use saccades for scanning surroundings and reading, right? So to that effect, and this is actually some of the earlier very interesting experiments done where we can actually track the human eye and see, hey, how things are, how the human is actually looking at different objects. And this is actually 2 seconds of the observation for a particular example that I'm showing here. Now the question is, can I use these kind of concepts, and would that be more robust? And the reason why it's going to be more robust, hopefully it's going to be clear soon, is the fact that, hey, if I now take an original image and I have to train it in a little bit different way, right? So if I take an original image which has a dog and a cat and a human, is it possible that I actually, learn some of these features of interest, in this particular case, the dog, the human, and the cat, using some sort of a global context network? I'm not going to go into the details of it. It could be random also. And then at the end of it, once I've learned these objects, right, and I know the points of interest, and the points of interest can be determined again through saccades, could be random or could be using this global context network, then I can actually look at, starting point could be those points of interest, and I try to figure out what those objects are. And I have also an idea about the relative location of the object so that I can also be able to understand scenes if I need to. So to that effect, let's try to look at what the ventral stream then in my case would do. It's basically the what stream, which is the recognition functionality. I can start my glimpse right here as an example, and this is the extracted foveated glimpse at time t1, and then I actually do try to figure out, hey, that particular glimpse, does it tell me or does it prime my network into thinking it's actually the cat's ears? And if it is a cat's ears, and if I have some confidence in it, then I need to figure out, hey, I need to go to the right to figure out I can see the cat's eye or the whiskers or not. And then I go move down right, see, hey, the cat's eyes in some ways, and then I go further down and say, hey, it is a cat face. Now I can find the whiskers that I'm supposed to, and it is basically a cat. And I can come up with my bounding box for a cat if I do that. Now, using such approach for learning, what one can do for the fun of it, actually, we played it in our lab and looked at a bunch of images. These are all my students, and tried to figure out, hey, where that face of the student is and who the student is, right? So you can actually come up with a bounding box and say, hey, this is this particular person, and where they are, I can start with various glimpses that I have, change my glimpse size, and figure out where they are. Now, that also tells me that what I'm really trying to look at in these glimpses is basically some features. Some features that I'm familiar with, and based on those features, I try to grow my glimpse size so that I can see the entire object. And now, what we wanted to do is also try to see that what it does to some optical illusions. Now, today, if you give an optical illusion like that to a neural network, it's going to be completely confused, right? But we don't get quite confused in some ways. So what is that? I mean, how many of you see that as a rabbit? How many of you see that as a duck? So most of you see it as a duck. How many see simultaneously duck and rabbit? Actually, theoretically, you don't see simultaneously. You have to change your glimpses back and forth before you actually do that. You don't see it simultaneously. So the thing is that, question, of course, is using such an approach, can I now really think about these optical illusions? And again, the basic idea is that we humans also always look for features, right? You look at the sky, clouds you see. Yeah? If you see patches of clouds, somebody says, hey, do you see that human face? Somebody says, no, it's a dog, right? They actually have different points where they're looking at, and their networks are primed to actually see what they are trying to see with those features that they see. Now, if I now try, for example, my glimpse point right here, or I can start here, I'm going to see two different things. To that effect, actually, we looked at this example of a duck and a rabbit. And we have these fixation points, and what I'm showing in the right is basically what the bounding box tells me. And at the end of it, once my network is reasonably confident here that it's actually a duck. Okay? Now, on the other side of it, if I start my glimpse right here, and on the right, as you can see, at this moment, the network is reasonably confident that it's actually a rabbit. So again, trying to really follow what sort of we humans do in some ways, using this ventral and the dorsal stream. And it turns out I can actually look at features, and I can potentially, now look at the fact that, hey, what's going to happen to my adversarial examples? Can I do better with these kind of techniques of foveation saccades with these adversarial examples? So what we ended up doing is looking at and analyzed, again, the adversarial examples and say, hey, in a passive vision system, what happens is that if I do put a patch, and that patch that I put in there is an intentional patch, which is going to confuse this neural network to actually say it's actually not a bird, it's a butterfly. Okay? And then why, it's going to be clear. On the other side of it, what I do in my active vision system is that I can put the patch in there, but I have different points that I start my glimpses at. And it's an active vision system. And if I do have my glimpses at different points, each of those actually tells me it's a bird, which is a goldfinch. But on the other side, if I start my glimpse over there, right, and if I grow it, unfortunately, that becomes a butterfly, right? Why? Because that has some features of butterfly that my network thinks, and then when it has reasonable confidence it's a butterfly, it stops. Right? But in an active vision system, since I actually have my glimpses and I go around, I don't see the major object that I end up seeing is basically the bird, and that's why I don't get fooled in a lot of ways. And if it's a video, it's even better. And in general, we end up seeing on videos. So actually, if we do use some of these, as you can see as an example, the initial fixation point variation, the methodology that we have is what's called Falcon, and basically looking at this active vision system. As you can see, that different glimpse points do tell me it's actually a fish. However, if my glimpse starts somewhere here, it somehow gets confused and says it's something else, okay? Because I stop ahead of time. Similarly, other examples of it that, this is basically the fish, depending on, how many, the initial glimpses that I start with. This is basically an ostrich. But if my glimpse line starts here, it basically predicts what it is supposed to predict. But if I start my glimpse here, it predicts something else, and ends there. So with that in mind, what we feel is that certainly human vision systems are quite stable, and potentially one can use such methodologies to actually have less of these adversarial problems. Yes.
Were the adversarial inputs trying to move the focal points somewhere?
No, I'm basically, my eye movements really focuses on certain areas, right? And then I. No. See, what happens is that what I was showing with the human cat and the dog is that you actually grow your glimpse size, right? And try to figure out, you're priming your network. Your network is primed to be able to say, hey, this is my bounding box for a dog. I have enough confidence as a dog, right? In this particular case, let's say if you start somewhere here, it is basically trying to look at something else, gets primed with these features right here, and somehow, based on my training that I had, it basically says something else, and I stop there. But if I do multiple glimpses, then I don't have that problem. Does it make sense?
Yeah, I was just asking if the adversary tries to intentionally move you to look at areas where you will see the wrong results.
Right. In general, but what I was trying to do is that I take a particular image, and update my inputs in such a way that loss for that dog that I wanted to classify as a dog now becomes a bookcase. I try to
choose those initial spots to look at it. Right? How do you choose those initial spots to look at it?
The adversary basically is aware that you're choosing those spots.
No. Adversary, I think let's not look at it from the adversarial attack point of view. It's not quite an attack. It's difficult to attack, but you get fooled. Right? That you can actually come up with different ways of doing that. You can basically say that, hey, I'm going to take a cat and make it into a dog. You can try to say, I'm going to take a cat and make it into a bookcase or a butterfly, right? Depending on the laws that I try to have. Because my network has been trained in a certain way, right? And I'm actually changing my loss with my inputs.
Questions about how do you decide where to look, right?
So in general, we humans try to look at it in general, if I give you a large image, there are 3 cats in there. How are you going to do it? I said, hey, find 3 cats in the image, right? The first thing that you do is randomly look at if you can random glimpses. If you don't find it, then you scan. So it's basically your eye movements tells you how you're going to do it. And I can do it randomly in my network. I can do it in a sequential fashion in my network, and I can do different ways. I think it was, it's from, I think one of the data sets, and I don't remember what it is. I don't even understand what it is. Yeah. All right. Now, one other thing is that, just talking about these adversarial inputs, now let's try to look at it from a little bit different angle and say, hey, is it possible that, I can have mislabeled data, right? Can I detect mislabeled data? Or can I say, basically, can I learn completely from, can I learn human faces by looking at a data set which has automobiles? Does it make any sense? Can I really do such things? In other words, if I can really come up with some secure learning in medical field, for example, in a lot of cases, what happens is that we do have a lot of data, but I don't want to share the data. The data can be sensitive, right? But I would like to actually in some ways learn from each other, right? Is it possible that I learn from each other, but not quite share the data? There are different ways of doing that. And Chris was talking about some of this, I guess federated learning or distributed learning in some ways, and I can, learn using my, the derivatives that I actually propagate. But is it possible that I actually share a data set with you, and it's a sensitive data set, and I don't want to share it, but I want you to learn? In the medical world, that happens a lot. In the military world, that happens a lot. We were actually working with the British Army and the and the US Army. They wanted to share some learning, but not the data. So is it possible to do that? So that's basically a challenge. So the question, of course, is, a simple example could be, can I learn, handwriting digits from images of places? It's an interesting question to ask, and we'll try to see, can we do that? So here's an example of some private images. And I'd like to learn the faces of these private images, and I want you to learn too, but I don't want to give you the data set. So is it possible that I give you a completely different data set that you learn from, okay? But you still learn these human faces. So I give you a public image of places, and this is doesn't even look, I mean, there's an aeroplane, as you can see on the corner, right? It doesn't even look like that original data set. So, hey, can I learn from there? Now, this one is actually a little bit different. The last one was bioplausible, but this one, I don't know if it's bioplausible. We can't possibly do that. We can't learn these human faces from possibly these airplanes and all. So now the question, of course, is, hey, is it possible that I take these two images in some ways and synthesize and come up with a synthetic image which looks very much like this? Okay, it's not much different from this image. But if I now give you this image and I say, hey, with the different labels, properly labelize it, hey, is it possible that I learn this? So the basic idea is that they have to be these two are visually very similar. This is visually dissimilar. And this is what I'm going to be. That's my private data set. I learn from it, but I give you this data set to learn from with proper labels. Okay, that's the idea. Or not this one, I give you this particular one. All right, so how can this be achieved? So one simple solution, what one can do is it can, is to directly use the public images. Or in other words, I have trained my network, okay, that's myself, and I have trained it on the private images, and after that training, I actually take my public images, okay, that I have, and I go through my network, forward propagate to my network, and I get soft labels for these human faces. So if I take that and directly give it to you, these public images with the soft labels, you're going to get some sort of an accuracy. And that accuracy turns out is not too bad, but it's not very good either. So in other words, what I'm trying to do is, how is learning possible in this case? By really transferring the decision boundary from the network trained on the private image to the network trained in the public images. Okay, just 1 minute. And then what one can potentially say that, hey, I have private data, I have private data, private class 1, private class 2, and this is the decision boundary for that. I've really done nothing and take that public data set with the soft labels, and then my data lies here. Okay. It turns out it actually does a reasonable job, not very good, but a reasonable job. But if I go further now, is it possible that, take that data set and really perturb this sort of input images, which is my public data set a little bit, so that I can move things around better. And I can now learn better. So to that effect, I mean, this is basically just taking directly the public images and not doing anything. What we can see is that for, if you want to learn these handwriting digits, right? If you align it properly, right? As I mentioned earlier, with that tiny ImageNet data set, then you can actually get some accuracy, but not high, not very high. It is possible to get very, very high accuracy on this kind of MNIST data set. But if I now can do something else, I take this private images, I train my teacher model, right, which is basically my on the private images with the proper data that with a private data set. And then what I do is I take the public image, okay, and I get soft levels, as I said, mentioned earlier, and then I perturb these inputs, just like what I did in the adversarial case, right? In adversarial inputs, I perturb those images. Now I'm taking these public images, I'm perturbing those images to make it look like, or at least to be classified as the private data set. And if I do that, turns out it can actually get very good accuracy. So now if you really look at this MNIST, this is basically the trained, the data set that I'm playing with. We actually looked at various different public images and tried to say, hey, how good is it going to be if I use these public images and try to learn MNIST data set as an example. As you can see that they actually end up doing quite well. Okay? And it's actually, you can almost give for learning these public images, you can actually give those. Huh? So another question that you might actually have, and I'll go back to you, but another question that you might have is that, hey, rather than public images, can I take random images? Okay, and just by taking random images, by perturbing those random images using, the approach that I mentioned, actually what we do is we actually try to use batch normalization and try to map that. Can I take that and learn? It turns out you can, but it's not very good. With the Gaussian noise, just initially you can get something like this. But for MNIST you can learn, but for these other data sets, it's actually difficult to learn. Yeah. Okay. Yeah, you can, but you're not going to get really good accuracy in most of these cases, but you can learn some. But you have to perturb those images. So basic idea that I learn, but when I perturb, I try to match the batch normalization statistics of those private images and perturb those input images so that I can match that batch normalization statistics. Now, the final thing is that another one on the mislabeled data. So if some data is mislabeled, can I detect it? Can I say, hey, somebody perturbed my data set, put in, instead of a cat, it puts a dog. Is it possible to do that? And can we detect and remove mislabeled data? And this is actually, we're going to be presenting in ICML this year, but how do you do that? It turns out you can look at the curvature of the data with the loss. Okay? So now, in other words, if I look at the curvature of the loss with respect to the input data, and interestingly enough, high curvature means in some ways that that particular data probably doesn't belong to that distribution. Okay? But a low curvature after training really means that it probably falls within my distribution. Now, if it doesn't fall, there are two possibilities. It could be a high tail in a long tail distribution. And if it's a long tail distribution, it's almost like, you have learned red apples and you've only seen one, green apple. And then you've sort of memorized it. There's a difference between memorization and generalization. So you memorized it. Now that memorization is going to give you a high curvature. Also, if you think about it, if I mislabeled that dog to be a bookcase now, mislabeled it, then of course there's going to be high curvature for both bookcase and the dog for those cases. So I should be able to, in some ways, detect it, and then theoretically, what one can show that that happens. So conceptually, I probably don't have much time, but what can look at these curvatures and I can, figure out, hey, atypical samples in terms of the loss versus the input space look somewhat like this. Typical samples looks, more of a flatter minima. So by looking at how the minima is a flatter minima or not, and looking at the curvatures, you can actually potentially say, hey, am I memorizing? Are there mislabeled samples? And so on. I may not be able to distinguish between a mislabeled sample and a memorized sample, but the possibilities are there that I can say that those are the tail of the distributions. How do you calculate curvature? I'm not going to go into the details of it, but it's a little compute intensive. But if you do, calculation of these curvatures for each of those inputs, it turns out that you can actually figure out, hey, those are, what kind of inputs they are. Just to give you an example of it, if you take this data set, on the left side of it, it's actually from, in this data set, I mean, you can see that on the left side has low curvature samples, on the right side is high curvature samples. And in fact, some of these samples are not sort of understandable what they are. You can also look at, for example, MNIST data set as an example, and we intentionally included some examples which are mislabeled samples, like, as you can see, these are 3s, but this is a 5. The question was, can I detect that my data set has these problems? And in fact, indeed, it actually does figure out what those problems are. Similarly, in a fashion MNIST, I'm showing, highlighting some examples, and these are basically present in the data set, that some trousers are mislabeled as something else, as I'm highlighting there. So these are actually, again, mislabeled in some ways. Similarly, in CFAR 10 also data set, there are actually mislabeled samples, high curvature versus low curvature samples I'm showing. They're mislabeling. A good number of some of those are mislabeled. Now, the final question, and I'm not going to go into the details of it, the final question is, hey, can I unlearn some of these mislabeled samples? Or if they're corrupted samples, can I unlearn? Anybody has seen the movie Eternal Sunshine of the Spotless Mind? So that's what you're trying to do. Selectively unlearn. No, is it bioplausible? Don't know. But hey, can I do that? So it's, in some ways, it's basically the eternal sunshine of the spotless network. Okay. So can I can have mislabeled data. Can I unlearn, rather than taking this new data set, removing those data, can I really take this network and just unlearn those things that I've learned? So this is the actually interesting part. I'm not going to go into the details of the mathematics of it, but if it turns out that if I can learn in an orthogonal direction to what I have learned, then I can change my weights. So is it possible that I use that concept of properly projecting the gradients and learn or change my weights in an orthogonal direction to where I have learned, then I might actually be able to forget that. And those particular things which are some features which are specific to that particular object, but might exist in other objects, so the commonalities are not. So by actually showing that you learn in the orthogonal direction, or actually change your weights in the orthogonal direction, you can actually do that. So with that, I know that I've taken some extra time, but just wanted to give you an example of taking a 10% corrupt data. This is my clean data set, okay? And this is how the boundaries are between the red and the green, right? But if I corrupt my data, then it's might have learned it this way. And can I really take this corrupt, this input and, correct it? And Verifix is the technique that we developed by using actually changing some weights in the orthogonal direction of learning. That if you can do that, then you can unlearn and sort of go back to what your clean data set should do. All right, with that, I'm going to be stopping here, and parting thoughts. I still think there's a lot more things to be learned. Deep learning is still a black box, and trying to figure out different techniques to see how we can try to make things more robust. Right, let me stop here.
Such an interesting talk. Any questions from our audience? Yeah.
Thank you, Kaushik. The question that I have is, so this is for learning up of of image pattern and image recognition, and in that context. However, my question is, can it be broadened? For example, if you look at a process, let's say an assembly line, or data coming from an assembly line, can you look at the data and learn up, okay, that's what is going on with the data, that's what is going on with the assembly line, that process is wrong, and then broaden the scope?
Yeah, I personally believe you can. Basically, what we're really saying is that, hey, some of those, thing that we're looking at here is basically looking at the distribution of data, and if I can try to figure out if it fits in. That's one possibility. But then again, the thing is that you might have, if you look at the process, if you trained it, you said, hey, this is what I see. I train it on that. And one of the other things that you can do is that, hey, you can take some failures that you've seen and you can relearn on those failures or incrementally learn on those failures that you've seen. There's an area called meta learning and continual learning, so you can do some of those.
Thank you, Professor. Going back to your glimpse point, is the glimpse point determined through some algorithm, or is the glimpse point determined somewhat arbitrarily? In other words, is there some sort of magic symmetry points that can be determined algorithmically, or is it just kind of luck of the draw for every image?
Yeah, both in some ways. The thing is that in general, what one can potentially do is, I was showing this context network and I say, hey, what are the points of interest that I'm going to be looking at? And for that, I need a trained network. Okay? I have to train a network with which we call the global context network, which is going to tell me with very low resolution, what are the points of interest. Now, another way of looking at it could also be, for example, I was putting that question, hey, can I find out 3 cats in this large image that I have? And in general, what we do is we try to find out those cats, right? And randomly to start with, because it's maybe a large image, randomly I try to see if I can find. And if I find 3, that's fine. But if I don't, then I can go and look at. But again, also we can potentially use a context network in that case too, but that training sometimes might be difficult, or I might have to do sequentially in my saccades. Yeah.
Oh, thanks for a wonderful presentation. The thing that you mentioned about merging different data sets, especially in a secure and safe environment.
Not merging.
Oh, sorry?
Not merging.
Yeah, but just
I'm
working.
I'm giving you a data set to learn from,
Yeah.
which is dissimilar to my
one.
private data set, but you learn the same thing.
Yeah, so I'm actually trying to build an idea on that. Like, why do you see an application? Because one of the ways that people do this domain adaptation, for example, is to merge through different embeddings. Because if you don't have the data set, but if you can get the embeddings, which might not be as private and will be more anonymized and everything, people do that. And there are also applications of that in LMs, for example, as well. Like you can just, instead of merging different LMs, you can just merge the different embeddings itself, and then mixture of expert model to apply to gain expertise just from the embedding itself and not touch the data set itself. So do you think that that's a viable option in this case as well?
Yeah, there are different options. There are absolutely different options possible. What I wanted to show is that certainly you can learn from a completely different data set, which you may not be able to derive the original one from. So differential privacy is also important, right? Can I really make sure that I have that along with this? So that was the idea. One is visual dissimilarity, and I should not be able to generate it from my data set.
Thank you.
Okay, thank you, our speaker, one more time. We're gonna have